Greetings, listeners from around the world. Jordan River here, back with more GrowCast, increasing bioavailability. Today, we've got Nick back for a nutrient deep dive. We're going deep into humic acids this time. That's right, we talk about what plants do, how they sequester carbon from the air and essentially put it into the ground, and what all these carbon, humic acid, fulvic acid substances do for us and our plants, along with how we can better utilize them. This is a great episode. I know you're going to love what we have planned for today with Nick. Before we jump into that, though, shout out to AC Infinity. That's right, acinfinity.com. Code GrowCast15 now saves 15% across the board at AC Infinity. They're trying to send you directly to their website now, and we are encouraging you to use code GrowCast15. You'll save 15% no matter what you buy, and orders $99 or more get free shipping. So go straight to acinfinity.com and use that code GrowCast15 to get yourself a new Grow Tent kit. AC Infinity has everything you need to succeed. They've got great build quality. They've been making fans for a long time, best fans in the game, and now you can save 15% on all of their awesome items with code GrowCast15. Once again, it's acinfinity.com. Use code GrowCast15 for 15% off. Free shipping on orders $99 or more. And if you're still ordering on Amazon, use code GrowCast for 5% off there. Thank you to AC Infinity, and thank you guys for using our codes. It supports AC Infinity, it supports us, and we appreciate you helping keep the lights on. All right, let's get into it with Nick. Thank you for listening and enjoy the show. Hello, podcast listeners. You are now listening to GrowCast. I'm your host, Jordan River, and I want to thank you for tuning in again today. Before we get started, as always, we urge you share the show. Turn someone on to GrowCast. We're on Spotify. We're on YouTube. We're all over the place. Turn on a grower or turn on a smoker to growing. It's how you can help us in our mission of overgrow. Make sure you're subscribed. GrowCastPodcast.com for all the things like the classes, the membership, the seeds. It's all there. Special thank you to all the members who make this possible. Today, we are back on the deep dive train with none other than Nick from Rooted Leaf on the line. What's up, Nick? How you been, man?
Jordan, I'm doing pretty well, man. How are you?
Doing excellent. Loving these nutrient deep dive series as always. It's some of the fans' favorite. And today we're doing something a little bit different with humic acids. Really, really excited to dive into today's episode on humics and fulvics and organic acids and all this fun stuff. Before we get into it, though, Nick, what have you been up to, man? It's been a minute since we've spoke. Are you just working on Rooted Leaf? Have you been traveling around? What's going on?
Yeah, I mean, things are staying pretty busy over here. You know, as we kind of enter the fall time, we're staying fortunate enough to stay really busy here at the plant. So I'm doing a lot of manufacturing. We've got some cool stuff in the works. We're going to go out to Massachusetts for the Harvest Cup that's coming up on, I think it's the weekend of November 9th and 10th. It's that Saturday and Sunday. So if anybody on the East Coast is listening to this right now and it is not after those dates, please come check us out. We're going to be at booth 601. You can't miss it. Right when you walk in, we're the very first booth on the right-hand side. So come up to the booth, say hi. We're going to have some GrowCast RLA t-shirts. And if you mention this episode, just tell us your size and we'll sneak you a shirt for free.
Oh my God. Custom t-shirt just for mentioning you're a GrowCast listener. Rooted Leaf, you're so good to us, man. I appreciate it.
Absolutely. I appreciate these deep dives, man. It's been a while since we've done some of these really deep dives. You know, we did the nutritional elements first. Now we're kind of shifting gears a little bit and looking at some other types of nutrients, which I'm super excited about.
Yes. I mean, like I said, this is some of the fans' most requested series. Really, really, they like this stuff, Nick, and you make a good product, man. There's a lot of people having good success with Rooted Leaf in the membership and in the community. So thank you, Nick, and thank you, listeners, for using code GrowCast. Saves you 20%, and it helps us keep the lights on. So it's a great partnership, and I'm excited to get into today's episode, man, because humic acids come up all the time. I think for a lot of lay people like myself, they're just kind of like a catch-all for like, yeah, it's like humic acids. It comes from humus, you know, like the soil, and it's just magic. That's what everybody says. Like, it's magic. It helps with this uptake, and it keeps away the bad stuff. And it does. You got a sore on your leg, you use the humic acids, everything clears up. I'm excited to see, you know, how specifically they work and how you can break down to us why they're so essential and useful, especially in a line like Rooted Leaf. So let's start the way we always do with these nutrient deep dives and just talk about what these are. What are these organic acids? What are these humic substances? And how do they naturally form out in nature?
Yeah, that's a good question. You know, there's a couple of different entry points, I guess you could say, and depending on the angle that we take to start the conversation off, we'll end up going down any number of deep dives and rabbit holes because humic substances are very complex, but there's also aspects about them that are simple. So maybe we should start by first establishing what are some of the simple ways to understand humic acids. And the idea basically is as follows. When plants are growing through their photosynthetic activity, really what they're trying to do is capture carbon out of the air. They're using the power of the sun. They have water as a fuel, and they've kind of figured out this really clever way to pull carbon out of the air. In its default state, the carbon is always going to be oxidized because we've got so much oxygen in the air that you and I are breathing. It's about 200, maybe 210,000 parts per million compared to about only 420-ish ppms of CO2. So there's a lot more oxygen than there is carbon dioxide. And this creates an atmosphere or an environment because it's so rich in oxygen that things tend to exist in oxidized forms, that oxygen really likes to steal the electrons. And so plants have this problem or this challenge they have to overcome. It's how do I take this carbon that's oxidized in the form of CO2 out of the air, and how do I reduce it through photosynthesis, and how do I really capture and store it over long periods of time? And this is where humic acids kind of come into play. Because as plants photosynthesize and they produce things like root exudates, those root exudates may actually contribute to building up organic matter in soils. And what this means is that they're pulling the carbon out of the air and they're figuring out really clever ways to make those carbon bonds very stable and very persistent over long periods of time. They resist oxidative degradation and they hang out in the soil with a particular arrangement of bonds that is a source of trapped energy. It's potential energy versus kinetic energy. So over long periods of time, what ends up happening is as the plants grow year over year, there's more and more organic matter that progressively gets sunk into the soil. And over a very long period of time, this combination of root exudates that are being produced, the activities of microbes and fungi, and also the remnants of all of them, plants, as they die, they'll drop the leaves. Those contribute to humic substance formation. Certainly as microbial colonies turn over, there are carcasses and there's remnants of microbes that used to exist. Those can contribute towards building up humic substances in soils over long periods of time. And same thing with fungal colonies as well. When the actual fungi, the mycelial network is growing, they too are capable of producing compounds like polysaccharides, for example, that will kind of promote soil aggregation, and it will form clumps in the soil, which is a very desirable property to have. If you have a very crumbly soil and it can hold on to water very well, it just kind of contributes to the overall physical properties and chemical properties of the soil. So, to tie this back into humic substances, simply put, it's just the result of what plants and microbes and fungi do in coordination with each other over very long periods of time. It builds up organic matter in the soil. It's very slow to break down. And so it kind of contributes to the building up of carbon. Now, I should also mention that there's physical properties that I'm kind of talking about with just the sequestration of carbon from the air and burying it into the soil. But there's also some kind of chemical properties that are associated with humic substances too. And, because by definition, humic substances don't have a specific molecular formula, their specific composition is going to vary greatly depending on a few factors. Like we just talked about, the plants that are growing, well, which plants, where are they growing? If they're growing in northern regions versus equatorial regions, there's different species of plants, and those plants produce different exudates, and those exudates have different molecular formulas and different rates of degradation, different chelation capacities, all of these wonderful things. When that stuff gets buried into the soil, it contributes to this weird property that there's no two humic substance fractions that are really going to be the same. There's some that are going to be similar enough, but certainly the further and further out you go and you kind of look at a global scale, all humic substances by definition are different because they're ultimately made up of plants. So there's a huge amount of variation that can occur on the specific chemistries of root exudates, soil chemistry. Is it a clay soil? Is it, subject to floods? Is it rich in organic matter? Are there microbial and fungal activities? And if so, to what extent? All of these things will contribute to the formation of stable residues that accumulate over millions of years. And as the total pool of organic matter increases, so too does this chemical diversity. So,
Jesus. Okay, so I have some stupid questions to follow up with. You ready?
yep.
So when I'm using my bottled humic acids, a lot of times it comes from things like lignite, leonardite, these things. And my understanding is that that is just like really ancient, I don't know, maybe petrified or fossilized humus.
Yeah, particularly with leonardite. It was named after a researcher. I believe he was a professor at the University of North Dakota. And I think it was back in the 1950s or something like that. He had stumbled across this realization that you could use really low grade coal that wasn't quite suitable for combustion. It didn't have enough hydrocarbon content inside of it. So it wasn't really useful for oil and gas refining. You couldn't really pull much out of it. It's just like trying to juice a piece of bread. There's not much to begin with. So he instead figured out a way to turn it around and make a soil amendment out of it. But kind of like I was just talking about, humic substances can vary greatly. And as the humic substances undergo changes over long periods of time, there's non-biological transformations that occur. I just mentioned some of the biological transformations, like what are the plants specifically, which ones are they, what are their root exudates, what's the microbial and fungal situation like. All of these things are biological factors. There's also non-biological factors like the exposure to sunlight, oxygen, moisture. This exposure to the elements causes transformations that create reactive species, which will spontaneously interact with each other and then result in sort of, in most cases, it's actually kind of a simplification of the system. So they tend to be like the humic acid fractions or the parent material, like the leonardite, for example, and other deposits. If you're taking the exterior layer, the one that where the surface actually meets and touches the atmosphere, that's going to be the site of the greatest weathering and the greatest oxidation. And so your degree of biological activity will actually be lowest because all of the functional groups that are involved in the wonderful chemistries of humic substances are going to have been broken down over periods of perhaps millions of years, as that layer specifically has been exposed to oxygen. But the deeper you go inside of the parent material and the further away you get from exposure to oxygen, the less chemical weathering has occurred. And now we're looking at things with a higher degree of biological activity. So,
Whoa.
yeah. I don't know if that answers
That's
your
wild.
question.
Okay. No, that was good. Yeah. I'm all the
totally
way
just
there.
off track there.
And I know that was perfect. And I didn't know about the Leonard. I didn't know it was named by a scientist named Leonard. I used to watch Big Bang Theory. I remember that guy.
That's weird.
Now, the second question, this was the actual stupid question I was going to ask. Then you hear about these other humic acids like, oh, this is seabed derived or lake bed derived. Now, stupid question. Why is it down there? Is it because that was once a place where plants grew, or does the sea actually contribute to the humic acid from the sea?
I guess in the context of, in order for humic substances to form, you need plant activity. That's the first and foremost thing, because if you just remove plants from the equation, then you rewind the clock by about 500 million years from current day, the planet looks very different than it does right now. We actually don't have any soil on this planet. We wouldn't recognize it as a planet. It's just a bare silicate crusted rock with no organic matter in the soil because all the carbon is in the air, and along comes these plants. And, particularly with the bryophytes, once they got established, they started literally eating the rocks and converting them into soil. And so all soils on this planet today, it's very widely accepted that their soils are quite literally the product of photosynthesis over 500 million years or so, roughly, or maybe even a little bit longer. But the point I'm trying to make ultimately is that the humic substances, in order to form, they need plant activity. And so whether that is sea plant activity like kelp, it could even be single-celled algae to some extent, I would imagine. But yeah, all of that stuff, as long as there's carbon being produced and carbon being sequestered and stored over long periods of time, you're going to get these types of transformations. But, more so to the point, I think what like the seabed or the lake bed reference is saying is that, hey, this stuff's been buried for a really long time. It has not been exposed to oxygen. The chemical environment has been very pristine in terms of preserving the functional groups on the humic substances first. So for every single gram that you pull out of this untouched material that has not been weathered or oxidized or subject to change, the higher the degree of concentration is. You may find 1 gram of this ultra rare, super highly preserved humic acid may outcompete 10 grams of the standard leonardite stuff.
Wow. Okay, so you're confirming a lot of what other guests have said about like differing qualities, but you're really highlighting the point. It's not just like no, it's not just a couple of these. Every single humic acid substance varies from one another because it was created over eons under different conditions. This all makes perfect sense. Before we go any further, another quick question: what about the harvesting or production of these acids, whether it be from lake beds? Let's take a look at them in totality. And this goes for what rooted leaf produces and all of that. Is it different than a lot of the mineral mining where it's like not super sustainable and stuff like that? Is this an abundant substance to be using in a fertilizer?
Yes, absolutely. The rate at which they accumulate is very, very slow, but the effects that are seen from the responsible utilization and really just the offsetting of other, conventional fertilizer costs, for example. I'm talking about like environmental costs, because
Right.
it's very environmentally costly to manufacture nitrates and phosphates and sulfates and so on and so forth. But a lot of companies, and to be fair to them, a lot of the companies that are doing this on a global scale, like the nitrate manufacturers, some of them are very, very efficient, especially ones like Yara that are based out of Europe. Like they do a really good job already, but there's still a cost that's associated with it. So, when you're looking at the total cost of applying the humic substances, the cost to benefit ratio is very much so in the favor of the farmer at that point.
Wow.
And for the planet at that point too. I mean, yes, they take a very long period of time to mature and form and develop and get to the right spot, but we have abundant amounts of them. And we can, to some extent, even create them over shorter periods of time with utilizing certain types of technology to help accelerate the process of humic substance formation. I think biochar is maybe just kind of like this loose thing that comes to mind, even though there's, distinct differences between biochar and humic substances that we won't get into today, but I'm kind of like just suggesting and pointing at the fact that there's a way to utilize them, even though they are considered a limited resource. The cost to benefit ratio would be so greatly in our favor. It's almost like we have an abundance relative to what we actually need.
Wow, that's very, very interesting. And yes, I would like to do a whole deep dive on biochar, but that's a different episode.
Mm-hmm.
Okay, let's move on to these points here, these lovely points that we have laid out. So here's one that comes up a lot. Humic acids are the same as fulvic acids, just smaller. I'd love for you to talk about all the different types of humic substances and then humics and fulvics and how they differ.
Yeah, so humic acids and fulvic acids are oftentimes lumped into the same category, but there are some differences between them. Humic acids, generally speaking, have higher molecular weights with more complex structures. Those complex structures tend to be less reactive than fulvic acids. They're a little bit more stable in the soil, which is why humic substances contribute to long-term soil health, is specifically because they're not reactive, they're stable. And sometimes you need to build stability in the soil. You need to build predictability in the soil. So humic substances can function to achieve that. The stability and lack of reactivity is what contributes to these long-term benefits that we've been kind of talking about. But having said that, they do participate in various chemistries, such as nutrient chelation. It's just that the presence of these repeating chains of these ring-like structures makes them resistant to degradation. So fulvic acids have lower molecular weights. They tend to be a lot more linear with fewer ring-like structures or fewer aromatic rings in their molecular formulas. They have more of these linear skeletons. And along this linear skeleton, there's various branches that fork out and lead to these functional groups or active sites where things like electron transfer and acid-base chemistry can occur. So this is why fulvic acids have a higher amount of biological activity. It's because these functional groups that participate in redox chemistry and acid-base chemistry, they're kind of like vital to the heartbeat of a plant. And so if you supplement these fulvic acids, it really just helps the plants achieve the most basic fundamental primary metabolic processes that plants are capable of achieving. That's why the effects are systemic in the sense that every single process within the plant will benefit from being exposed to fulvic acid, because the most basic of all plant processes, which is electron capture, transfer, storage, and then acid-base chemistry, all of them get a nice little boost when they're exposed to fulvic acids, because again, it's those functional groups that plants produce anyways. And if you really think about it, it makes a lot of sense why plants would produce these functional groups, bury them in the soil, and then store them, because if the plant's goal is to reproduce successfully for the next generation, maybe one of the functions of the humic acids that are buried in the soil is actually to supply these exact functional groups for the next generation of plants as it grows and it matures.
Whoa.
And is supported by the very same microbes and fungi that not only participated in helping that previous generation of plants grow, but also make the humic substances themselves. Like I mentioned, fungi, they secrete polysaccharides into the soil that contribute to crumb formation and aggregate formation in soils, which is a beautiful thing because now you've got this like little pocket of nutrition. And if you have a plant, a young plant that's growing, and not just any young plant, but the next generation of the same exact species of plants that the microbes and fungi participated in helping to grow, like it makes all the sense in the world that these functional groups are shared between not only plant species, but also from generation to generation. They're putting the stuff in the soil to allow the next generation to take them up and do an even better job than the previous generation did. This is why soil tends to build up over long periods of time.
It's just interesting. It's like it almost seems like the humic acids are like part of like they're intelligent. Like they're part of the, you know what I mean? The soil itself becomes this aggregate living thing. After a while, it's not just like, oh, here's the bacteria and here's the protozoa and what they do. It's just so much more complex than that.
Yeah.
But what you're saying is they do humics and fulvics doing similar jobs, but different specific functions. So would you say okay, this goes into like everything you said about humics being different and now humics and fulvics having different functions. Is there a benefit to having humic and fulvic and organic acid diversity, just like we take a look at microbes and microbe products and everyone says diversity is key? Is it better to have more different types?
That's a good question. I would say, generally speaking, the answer is going to be no, because most humic substances, and I know it sounds a little bit ironic because I just got done talking about how, all humic substances are fundamentally different, but this is true by definition of how we define humic substances to be. Of course, they're going to be different depending on which plant species made it and so on and so forth. But ultimately, the functional groups that are preserved and the structural groups that are preserved tend to be actually shared among plant species. So we see repeating motifs like the methoxy groups, for example. We see a lot of like phenolic compounds inside of humic substances, which are ring-like structures. And those are kind of ubiquitous across all plant species. So it seems like there's a general benefit from a specific structure function kind of relationship. But I will say that in some cases, because humic substances can differ based on like surface area, for example, and that surface area might lead to an increase of water retention. So you may find, generally speaking, humic substances can increase the water retention capacity of soils by about 5 to 10x, let's just say, because humic substances and their surface area and the whole water bridging phenomena, which we'll get into here in a second, they tend to trap water and hold it very well. Humic substances are like sponges for the soil. And it might be true to say that some humic substances are a little bit more spongy than others. Other humic substances may have a little bit more spark to them, meaning more functional groups, more electrolyte activity. They're technically polyelectrolytes. And so you have these like minor differences in functions that are pretty much shared regardless of where the humic substance came from. If that
I got you. So categorically, they do certain things, but some just have different flavors, maybe a little bit better at this or that. So you're not getting as much benefit from mixing together all these different sources than you would say with like microbes that might be doing totally different things. One might be liberating phosphorus and another one might be raising and lowering pH more effectively. Humic acids is just, they're more alike.
Yeah, and it's again specifically because of those structural and functional groups, they tend to be shared. There's carboxylic, there's hydroxyl functional groups. These tend to be in higher concentrations in fulvic acids, which again explains their ability to participate more in nutrient chelation, electron transfer. There's also something, like really, really deep dive, crazy rabbit hole here to the side, which we're not going to go down for sure. We don't have nearly enough time. But, there could be something, and I'm saying this because something that you said specifically earlier kind of sparked this, which is to say that humic substances and really fulvic acids can actually be used for intelligent capturing, transmitting, and reading/writing of information in the soil. And it has a lot to do with the functional groups that are present inside of fulvic acids. They can kind of hold a charge. And much like there are pigments in plants like chlorophyll, for example, it's an antenna pigment. So it absorbs one, narrow frequency of within the visible light spectrum. Well, plants are also sensitive to other types of frequencies besides light. And I think the idea here that I'm trying to get at is that they are writing information, they are encoding information into the soil, and the humic substances act like a hard drive to capture the information. and the conditions of the soil around it are captured within certain types of information. The fulvic acids could be like the RAM, just that short-term memory where things are written really fast and they're read really fast, and so on and so forth.
Jesus, that's really cool. And then the hard disk space is more like the humic acids.
Yeah, because there is information about soil chemistry stored inside of humic substances, because part of that information is being read and written by microbes and fungi as well as the plants themselves that are dealing with the aerial portions of, the environment and the atmosphere. So microbes and fungi will kind of read it and write information as it relates to soil chemistry, whereas the plants themselves, as they in the actual process of depositing humic substances into the soil, it's a direct reflection of what the aerial conditions are like. And I know it's a far out concept. I'm not saying that this is like a hard fact and there's mountains of evidence supporting this or anything like that. This is just kind of like, hey, if you look at it from this angle, it makes a lot of sense. So yeah, humic acid's definitely very complex. It's not just about, functional groups like we've been talking about, or acid-base chemistry and electron transfer, water bridging, nutrient chelation. These things are pretty fascinating in their own right, but I'm more interested in this like larger concept of plants treating humic substances like hard drives to store information, to access information that's been stored elsewhere, and to communicate with each other using electrical signals. So,
jeez, that's insane.
Not to go too deep.
It's like the brain of the soil. No, that's great. That's great. Well, what about from a cultivation perspective? You mentioned like soil conditioning, which is something I've definitely observed as somebody who uses humic acids, and what it does to like the texture of the soil is very interesting. But do you want to talk about some of the stuff like uptake or other major functions?
Yeah. With fulvic acids, like I was saying earlier, because they've got no methoxy groups, they have fewer phenolic groups, but they have higher amounts of the carboxylic and hydroxyl functional groups along those linear skeletons. And so as such, as a direct result of this, they have a much higher cation exchange capacity. So if you're looking at doing things like correcting nutrient deficiencies rapidly within plants, the best bang for your buck is going to be to use a fulvic acid. Even if that fulvic acid is derived from leonardite and it doesn't happen to be a very high quality one, that's okay. Fulvic acids still, generally speaking, have a higher degree of biological activity, and they will assist with micronutrient deficiencies or even macronutrient deficiencies, things like that. Yeah. Humic substances, on the flip side, will tend to operate over longer periods of time. So if you're thinking about making a soil, or you want to mix something into your cocoa because you think the cocoa needs to hold on to minerals a little bit better, you're like, gosh, how can I increase the CEC of the cocoa? Getting a good quality humic and then maybe just even soaking the cocoa once. Like with our root anchor, for example, we've had people do it in the past using 10 mils per gallon to soak up or hydrate those cocoa blocks that come compressed, because oftentimes they need to be submerged and hydrated anyways in order for them to actually be fully fluffified. That's a technical term. If you have to fluff up or you have to hydrate or expand cocoa, it could be a good idea to use root anchor at about 10 mils per gallon, or if you've got another humic acid source, it could be a good idea to do that as well, because it's going to contribute to that long-term soil chemistry, because it has those phenolic compounds, more derivatives of lignin that are really stable over long periods of time. It'll tend to physically imbue itself into the cocoa fibers, and it'll dot the exterior of the cocoa fibers with a higher concentration of active sites. So now the CEC of the cocoa has gone up, meaning it can hold more calcium without leaching it out. It can have a better profile of calcium to magnesium to potassium, so you don't have to worry about deficiencies or lockouts as you scale up the EC that you feed your plants, because cocoa definitely has a need for an improved CEC in most cases, from what I've seen. So
wow. So soak in root anchor with some humic acids because of that heavier molecular structure and what it does to the texture of your medium. You would opt for humic acids there, versus, like you said, if you're trying to correct a deficiency, or like we see all the time, man, micronutrient deficiencies popping up because they're needing such trace amounts. If you happen to have some cultivar that just loves to eat manganese, you got to bump up that manganese. There, you would recommend adding a fulvic acid because it's more of a quick exchange and a short-term thing. Did I get all that right?
Yeah, and the complexes or true chelates, depending on the specific molecule that we're looking at here. But anyways, I'm going to use the term chelated at large, but more technically, it would be complex or chelated, depending on what we're talking about. But the chelated forms of these elements themselves are a lot more available across foliar surfaces, because fulvic acids, once again, they are plant recognized substances. The plant's like, oh, I know what this is. I'm in the business of making this anyways. And in fact, I would make this exact same thing and I would move it to the soil and I would bury it there. So of course fulvate chelates tend to be a lot more soluble across leaf surfaces. So if you do run into something like a micronutrient deficiency, manganese is a good one because you brought it up. Well, most manganese is going to get metabolized in the aerial portions of the plant anyways, because that's where the oxygen evolution complex is. That's where the water splitting activity happens. And think about the function of manganese like an alternator in a car. As the car is running, aka as the photosynthetic engine is operating in the plants, the function of manganese really is to resupply electrons back into the electron transport chain, much in the same way that an alternator supplies electrical current and flow back through the system so the battery does not get decharged. So when the lights are on, manganese is active in photosystem 2. Yes, photosystem 2, because that's the activities of the oxygen evolution complex are associated with PS2. But so yeah, if you're deficient in manganese, most of the manganese is going to be needed at the leaf surface anyways. So if you used a fulvic acid along with some kind of manganese micronutrient, you can even soak, if you've got like manganese sulfate or something, just a powdered form, you can soak that directly inside of a concentrated fulvic acid and then dilute it and then spray it, and you'll get good results that way.
Man, that is absolutely brilliant. I'm going to lock that one away. And is that true of many micronutrients? Is that like the case with a lot of those trace minerals?
Yeah, it's true that a lot of the micronutrients, they're used for catalytic functions that tend to be more localized in the aerial portions of the plants, because the roots themselves, while they do have a need for micronutrients for like redox, regulation, and antioxidant defense mechanisms, these are present at every single cell in the plant. So of course, those elements will be like pretty well spread across the plant. But generally speaking, it is true that the aerial portions are subject to higher amounts of oxidative stress. So they're going to need more micronutrients, such as the ones responsible for, redox stress response. And then also more of the minerals themselves, like calcium and magnesium, potassium. Certainly calcium gets accumulated in the roots, but in the aerial portions is where it tends to flow pretty rapidly. So yeah.
Wow. Especially probably when you're turning up your light super bright, your high powered, expensive Ferrari of a grow light, driving that engine fast. Growcast membership. Come and join the best community in cannabis cultivation. I would love to have you inside. We make growing fun and easy. If you're running into any problems in your grow, we can diagnose your problems accurately and provide you with solutions that work. The last thing you want to do is run to Google with your grow problems. There is so much bad conflicting advice out there. Come jump in our membership, jump in our plant problems channel. We will walk you through it and hold your hand and fix any problems you have. Plus, we have a thriving community for you to connect with, people to trade cuts with and seeds. We've got live streams and giveaways and contests. We've got the Grand Pheno Hunt going on right now. Someone's going to win $1,000 for hunting through a pack of our seeds. And we've got another round 2 of the Grand Pheno Hunt coming up so soon. You're going to want to get in membership just to see what it's all about and to make sure that you get it on the next Grand Pheno Hunt and all the grow challenges we have going on. You can find it at growcastpodcast.com/membership. Get on in there. You will not regret it. Send me a message that you heard about this ad. I'll even refund your join fee so you can enjoy 30 days free. And like I said, get on this Grand Pheno Hunt. It's one of the greatest things we do. The next one's going to be even bigger, and someone's going to win $1,000 just for growing along in Growcast membership. Shout out to Hygrozyme for sponsoring the Grand Pheno Hunt. We love Hygrozyme, and they are supporting us as we make some fun contests and grow-alongs for the community, because that's what it's all about, supporting the growers, supporting the cannabis community, and making all of this easy and fun as it should be. So special thank you to Hygrozyme, special thank you to all the members and all the Grand Pheno Hunters. What are you waiting for? Come and join us. We've got the greatest community in cannabis. Growcastpodcast.com/membership. We'll see you there. What else are we talking about here as far as functions of humic substances? Talk to me about chelation and also, I don't know if it's called sequestration, but like, again, what they tell you at the grow store is, this will help the uptake of the stuff that you need, and it'll even prevent the uptake and bioaccumulation of some of the nasty heavier metals. You want to talk about that relationship?
Yeah, for sure. And again, this goes back to the purpose of some of these humic substances being formed is specifically because the plants are trying to mediate what's going on in the soil with what's going on in the air. They kind of exist in this plane between the two, right? They're taking carbon out of the air. That's where the sun is. That's where the air is. But they have this entire underground life that they have to pay attention to and take care of. So it makes a lot of sense if the plants are able to funnel photosynthetic energy down into the soil and kind of build the soil matrix up from there, because the rate at which they can increase soil formation far exceeds that at which soils naturally break down through phenomena like chemical weathering or microbial oxidation or fungal activities or things like that. Those tend to happen over very, very, very long periods of time. So nutrient chelation and heavy metal detoxification follow kind of the same principles of the plant is trying to do something in the soil. Hey, I need more of this, and hey, I need less of that. And using the power of the sun, they're capable of creating metabolites, which when they are secreted into the soils as root exudates, can do either one of those two things. They can grab more of the calcium or the magnesium or the potassium that it needs. Or on the flip side, the molecule can be made with such specificity that when it interacts with aluminum in the soil, it will actually decrease the solubility of aluminum and thus make it insoluble in water. When things are not soluble in water, it becomes very difficult for plants to take it up. So this is one effective strategy at which plants that are actively photosynthesizing and actively growing, they're monitoring the soil conditions and they're saying, okay, there's a lot of aluminum going on here. So more of the carbon flow and the photosynthesis power, that reduction power, will flow out in the form of these molecules that deal with heavy metal detoxification. And those will, over long periods of time, accumulate inside of the soils as part of small fractions of the humic substances at large. But again, it's the same functional groups. It's the same kind of chemistry. It's just a different shape to that molecule so that when the aluminum comes along, it's effectively captured and the molecule itself is not soluble in water and the plants cannot take it up. Now, on the flip side, if we were talking about calcium or something that the plant wants more of, the exact same idea is true, that the root exudate, which comes out, now has a function of binding to the calcium and increasing the solubility, because a lot of times in soils, calcium is not very soluble in water. Calcium sulfate or calcium phosphate, rock phosphates, bone meals, things like that, they tend to not release calcium in very high concentrations. So plants have a vested interest in accessing more calcium. So they excrete certain organic acids and organic compounds, flavonoids, things of that nature with the proper functional groups and ability to bind to these minerals that they do want, thusly increasing their solubility.
Jeez.
And then when the water comes, it picks up because the solubility has increased. And now plants are getting more of the calcium that they want. And they're also getting less of the aluminum that they don't want and other heavy metals. I'm just using aluminum as an example because it happens to be one of the most abundant elements in the Earth's crust, yet it is one of the most damaging elements for plant metabolism. So plants have figured out very smart and clever ways to access what they need inside of the aluminum silicates that make up a huge percentage of the Earth's crust, while excluding and blocking the aluminum from being taken up and still getting all of the calcium and potassium and magnesium and all these other elements that are present inside of these aluminosilicates.
Wow, that is fascinating. Super fascinating. So I know it's personification, but basically what you're saying is the plant knows what it wants more of, and therefore if those carbon elements aren't there, if those organic acids aren't there, it kind of uptakes those heavy metals by accident. Is that kind of like, again, it's personification, but that's what it sounds like when that carbon is lacking.
Yeah. And I always tell people to think about plants like semi-permeable water pumps. They're not like perfect filters. They're not going to exclude things that they don't want, and they're not going to only take up the things that they do want. At a certain point, they're semi-permeable water pumps. Like if something is dissolved and if something is small enough, the pump is going to take it up.
Sure.
Plants do have some screens here and there. They've got molecular mechanisms. They've got transport pumps and things like that are very specific towards particular charges. But the point is that they're still semi-permeable water pumps, and they will, even if there is some soluble aluminum in the feed water that they're drinking and they don't want to take it up, they will inadvertently take it up. So now this comes back to the second half of the approach that plants have evolved over long periods of time. And we touched on this in an episode that we did about heavy metals. There's two ways that plants can deal with heavy metal toxicity. One is to limit the solubility. Like I just mentioned, some of these humic acids, they will bind, they will physically grab onto the aluminum and they will neutralize the aluminum. So it's no longer available as part of the soil solution. It's trapped, it's bound, it's not reactive, and it's not soluble. So it's just kind of hanging out there. It's not really doing anything harmful for the plants, and it's not really getting in the way of any kind of soil chemistry. So there's an important There's an important thing to clarify here, which is that we have a decrease in solubility as one of the driving factors for heavy metal strategies, you could say. And the second half is neutralizing the ionization potential. If the plant has picked up a compound, like if it's picked up aluminum, that may be okay if the aluminum is neutralized and it's not capable of interacting with any of the cellular constituents. So by removing the ionization capabilities of aluminum, plants can pass aluminum through their tissues with no reaction. So a lot of the soluble flavonoids and things that circulate in the phloem tissue, before they become root exudates that are pushed out into the soil and bind to aluminum anyways, those same compounds are flowing inside of the plant. So if there is a piece of aluminum that is flowing around inside of a plant, some of these molecules, the metabolites that are still inside of the plant, can actually bind to the aluminum, neutralize its ionization potential, and have it flow freely through the plant without actually causing any damage. And then at this point, even though the aluminum is soluble, it can still be accumulated in relatively high concentrations because it doesn't pose a risk of interacting with any of the cell constituents. A lot of the heavy metals, they tend to steal electrons. They're very electronegative, and so they like to just strip electrons away from stuff at a pretty rapid rate, which is why they break literally all the organelles get damaged within the plant. Cell walls can be damaged as well. So, exposure to heavy metals is quite damaging on pretty much any layer of plant metabolism, even out to like the whole cell. Just looking at the whole cell, it can be very damaging. So yeah, plants have this strategy using what would have become a humic substance or a fulvic acid or whatever it is. If you take that molecule and instead apply it to internal plant chemistry immediately, it can help neutralize some of these heavy metals. And then there are certain plants, I think like hydrangeas, for example, they can take up high concentrations of aluminum and sequester them in the petals. And the petals are just spots of very low transpiration. There's not a whole bunch of, phloem tissue activity. In fact, I don't think there's anything flowing back from the petals. I think the petals themselves are kind of like the dead end. It's at the very end of a dead end in terms of metabolism. That's where the terminal metabolites are sunk into, is in the petals. And so they can accumulate high concentrations of aluminum and there's no damage to the plants. Yeah.
That is wild stuff, man. And I've never had the picture painted for me like that as far as how heavy metals prevent things. Increasing and decreasing solubility. That was a big eye opener for me, just that analogy. And again, the water pump analogy that you've always used has been super, super eye opening for me. And it has helped me in my game with teaching people how to identify problems in their own grow. If you think about this plant like a pump and what makes it run fast and what makes it run slow and what it looks like when it's running too slow or too fast, it can really help you get a good picture. We're going to do a whole episode on how that pump runs and water dynamics and water quality. That's probably going to be our next deep dive, isn't it, Nick?
Yeah, definitely. It's going to be one heck of an opportunity for us to take a look at maybe some less conventional ways of thinking about water chemistry, and specifically if there's anything else going on that's a little bit more mysterious. A lot of it will be kind of like not really fringe at this point, just more like cutting edge science, but it really challenges the conventional way of thinking about water and water chemistry. One of the best ways for us to kind of lead into that is by looking at this phenomena of water bridging in humic substances. And we've kind of set the stage already to address this topic because it's a very well explored, very well understood property of humic substances. And we went through the functional groups that both humic and fulvic substances shared, which is those carboxylic functional groups and those hydroxyl functional groups. These are both capable of participating in a type of chemistry that interacts with water molecules in quite an interesting way. So water molecules are H2O, and they have these two hydrogens that are floating around that are capable of making hydrogen bonds and breaking hydrogen bonds relatively quickly. This is actually how water molecules kind of behave, bulk water, I guess you could say, like a glass of water. Most of the water molecules are kind of behaving like this. Well, there's this interesting property that humic substances have. It's called water bridging. And the two hydrogens, instead of just kind of floating around and constantly breaking and reshaping and forming new relationships with other water molecules in the vicinity, those two hydrogens tend to get locked into place at the active sites of some of these functional groups. So with the carboxylic and with the hydroxyl functional groups, that oxygen will attract the hydrogens. And now you have the situation where you've got these two hydrogen molecules that are kind of connected more or less. They're locked into place inside of the humic substance. And then you have the oxygen as a constituent of the H2O. The oxygen kind of hangs out on the exterior with its back exposed, and it creates this, because oxygen is more electronegative, it kind of creates this space for cations like calcium and magnesium and potassium to be attracted to. And now you have this pulling effect going on. So you have this, it's really fascinating what water bridging leads into. But basically the idea is that the two hydrogen molecules with oxygen in the middle of the H2O will actually physically make a bridge across two of the active sites, or perhaps even more, two or more of the active sites within a humic substance or a humic molecule. This keeps water molecules really close to humic substances. So if you've ever heard the idea that humic substances can increase the moisture retention capacity of your soil, meaning your soils won't dry out as fast, really good if you're living in a hot and dry area, that is one of the mechanisms by which this is true, that the water sits like an actual bridge and it resists leaching out from the humic substance. The humic is pulling it because these functional groups that it has are charged appropriately to attract water molecules. And once the water molecules are locked into place, they're way more stable. They're not going to just flow around. They're not going to just drop off the active site. They're not going to beat up and roll away. They're going to hang out and contribute to this hydration shell that's formed. And they're going to attract positively charged minerals, which is really good for sort of the electrochemical, electrostatic properties of humic substances. To have water chemistry factored into that is really fascinating. But the reason I'm bringing up water bridging specifically is because this concept of this bridge that's formed is something that we will take out of this conversation and apply to the next conversation when we're just looking at water molecules, rather than right now we're looking at water molecules and the interaction with humic substances and the functional groups and this water bridging phenomena that increases moisture retention capacity and increases nutrient chelation, all this wonderful stuff. The mechanism, what's actually going on here is really, really, really fascinating, like super intriguing. And we need to blow this super intriguing concept out into a full-blown conversation about water chemistry so that we can better understand water. But for today's topic, obviously being humic substances, it's just a nice little teaser for people that are listening and want more. Maybe you're a little bit thirsty for the next conversation. So stay thirsty, my friends.
I like it, man. I like it. Yeah, we were talking off air about that one. That's going to be a good one for sure. But back to these organic acids. Any other cool effects that, I mean, I know they do like a million things, right? Talk to me about any other kind of interesting factoids or functions of these, and as well how they operate within your line and why you incorporated them.
Yeah, I think we've gone through pretty good amount of information about, how humic substances work. I think maybe one thing that we could talk about is the mechanisms of the formation of humic substances, because they are pretty complex. And so the question that a lot of researchers have is, how are these substances being, how are they being built up over long periods of time? Because part of it is spontaneous, right? Just exposure to the elements, whatever the weather is doing, however much air there is. This stuff tends to drive changes in these molecules, whether you like it or not, and whether the plant likes it or not. They're going to change because the environment on this planet and the atmosphere changes things. But there's also something to be said about how microbes and fungi participate over very long periods of time to create humic substances. And a lot of it comes down to a couple of different categories of things that have been observed. One of them is lignin modification, because plants produce a lot of lignin. Trees, obviously, untouched forests with very large, very old trees. There's a lot of lignin that's been produced and will continue to be produced, but it's resistant to microbial decomposition. So partial breakdowns over very long periods of time result in the formation of the very exact same phenolic compounds that give humic substances their stability, like we were talking about. And these are kind of like the precursors, right? So now we have this operation that microbes are involved in, and fungi too, because fungi, for anybody that's ever seen mushrooms blooming out of a log, that fungi are really good at decomposing woody material. Well, if that happens underground and in the right conditions, this byproduct of those activities results in humic formation, meaning that microbes and fungi are actively producing building blocks through their metabolism. They're contributing it into the soil. And this lignin modification at large is one of the umbrellas, I guess you could say, by which major pool of substrates flows into humic substances over long periods of time. That's where phenolic compounds come from. And then there's quinone amino acid interactions. When those phenolics that we were just talking about spontaneously oxidize in the soil, because if the soil has good aeration capacity, there's always going to be oxygen present inside of the soil. Well, some of these building blocks get oxidized, and the phenolic compounds themselves are pretty reactive. So they tend to react with things like amino acids and proteins and even sugars. This is the Maillard reaction, but they interact with this complex soup of other molecular constituents that are present in the soil. And these reactions lead to the formation of these polymers, these more complex, longer chain forms of the humic acids that tend to be like repeating units and repeating motifs that we see over and over and over again. And then, like I mentioned too, besides just what the microbes and fungi are decomposing from the plants and all the leaf litter and all the woody debris and all the lignin, that's one flow. But another flow itself is, what are the microbes producing for themselves, and what are the fungi producing just by themselves? I mentioned earlier the sugars that are produced by both microbes and fungi, the biofilms. These exopolysaccharides do a really good job of creating crumbs and clumps, and they aggregate soil particles together, which is really, really healthy over very long periods of time, because then you get perfect consistency. You get good resistance to oxidation and degradation, and you also have high moisture retention capacity. You've got all these wonderful properties that are starting to be built up over long periods of time. So microbes and fungi actively producing in their own way. And then the last one is the Maillard reaction, which is just basically sugars and amino acids, as proteins and things of that nature are being broken down. There's protease enzymes that are actively cleaving some of the peptide bonds holding proteins together and releasing the simpler amino acids that make up those proteins. And during this process, if they're exposed to certain types of sugars, maybe the microbes and fungi are making these sugars and they're breaking down the plant proteins. Very, very common pathway here. Well, those two can come together. It's actually, the Maillard reaction is actually best known in cooking. When you cook a steak and you sear it, the Maillard reaction is, if you understand that, that's the Maillard reaction. This happens in soils. Obviously, it doesn't smell like steak cooking. It's a little bit different, but the same kind of chemical reaction occurs under the right conditions. You need a little bit of heat, but some of the Maillard reactions can happen spontaneously at room temperatures. Most of these Maillard reactions would happen during the summertime when the sun is out and about and the soil is actually quite literally cooking. This reaction, basically sugars from plants, microbes, fungi, these are reacting with the amino acids that are being produced as a result of proteins being broken down. And this is one of the ways in which humic substances can mineralize nitrogen sources, so that, because nitrates are very soluble, amino acids tend to be soluble, and they tend to be soaked up by organisms pretty rapidly. There's a lot of competition for nitrogen in the form of amino acids. Organisms don't really like to share it. So it makes sense why, if plants have excess nitrogen that comes down in the form of leaf litter or some other proteins from the roots or some other structures, that there might be a way to mine the nitrogen out of the decomposing leaf litter or the parent material and store it in the soil by mineralizing it. And this is one of the pathways, the Maillard reaction is one of the pathways through which that can occur. There are catalysts that are required in order to have these reactions happen. A lot of them are the micronutrients. So for the purposes of plants, the micronutrients and the way that those are used is perhaps a little different. For microbes and fungi, we do see that a portion of the micronutrients goes specifically towards catalyzing some of these reactions that result in humic substances being formed.
So talk to me about Brood Anchor, because that's the one that is working with the humics, right? Just really quickly before we go, I know we've done like episodes on this in the past as well, but talk about the humics in your line, Rooted Leaf. Again, rootedleaf.com, code GROWCAST.
Yeah, so Root Anchor is our humic acid meets a beneficial bacillus probiotic package, meets a licorice root extract, a fermented licorice root extract. And this is a wonderful package. There's also a whole bunch of seed plants in there as well. There's a very, very high concentration of humic acids inside of Root Anchor. It's about 10 pounds of raw humate per gallon equivalent. And it's a type of humic acid that is extremely biologically active. As I was mentioning earlier, not all humics are the same, even though generally speaking, they have the same functions. The humic acid that we're using, it's the full humics from BioAg. It's a very high quality humic acid that has a high amount of biological activity. So what we're doing is extracting all of the soluble humic constituents out with all of their active sites and their functional groups. And then we're infusing, I guess you could say, we're doing like a sort of a molecular chelation, although it's kind of a clunky term to use in this specific context. But, the fermented licorice and the sea plants, all of these have similar charges that fit directly into the active sites of the humic molecules. So it's almost like we're putting together a little jigsaw puzzle. The humic substances want, in their nature, they want to hold on to things of a certain charge. And the things that we're extracting from the fermented licorice root and sea plants, those get imbued directly into the active sites of the humic molecules. So now you've got this, humic that has the sugars that are good for microbes and fungi, all the prebiotic food sources, all the biostimulants that they need to grow. Those are physically attached into the humic molecules. They tend to resist degradation very well. And then on top of that, we put a dozen strains of beneficial bacillus microbes, all of which contribute to healthy soil chemistry, excellent root growth, good stability in the soil as far as microbe versus fungal populations. There's a couple of species of microbes that we have in there that are sort of known in nature to bridge the gap between microbes and fungi, because it's not just the microbes are working with the plants and the fungi are working with the plants. In reality, there's that third connection there too. The microbes and the fungi work with each other as well as working together with the plant. And that, I think, is something that a lot of probiotic formulations tend to overlook, because they either put the microbes or the fungi and they say, yeah, well, they outcompete each other and they don't, play nice. That's not true in the case of root anchor. We have certain species of microbes, bacillus microbes, whose entire existence it is to create a functional bridge to connect the activities of the fungi with the activities of the microbe. That way you get an extremely diverse profile of microbes in the soil, and you don't have to worry about them competing against one another. They all work extremely synergistically with each other, which I think is a very rare feature in microbiology.
I love the bridging of the gap, the water bridge of the gap, if you will.
That's right.
Between the bacteria, the fungi, and the humic acids. And just getting a better picture of what this looks like. The analogies always help me understand exactly what is going on with, like I said, these buzzwords that you kind of know and you hear about, but understanding how they actually work takes it to a whole nother level. So this was really cool, talking about nutrient uptake, carbon sequestration, what it does to the soil, and everything about humics and fulvics. Also the difference, like really now I'm going to look at those differently, and it's going to change the way that I give people nutrient advice, from the fulvics being a more quick fix to soaking the cocoa to foliaring the micronutrients. This was a jam-packed episode, Nick, so I got to say thank you.
Yeah, and just real quick, I want to mention one last thing. We won't get into a huge level of detail about this, but humic acids and fulvic acids are like kind of the two categories that are most familiar to people. There's kind of a third one that's a little bit more vague. It's called ulmic acid, ULMIC, and it's kind of in between the two. So I mentioned humic substances have large molecular weights. They are heavy molecules. They got a lot of ring structures inside of them. They're bulky. They take up space. They resist washing out. They're kind of fat and chunky and clunky, and that's good for soil chemistry. Fulvic acids are like sharp knives. They're very precise, linear, highly soluble. They tend to flow. They have a higher concentration of active sites. They're more reactive. In between the two of them, and I just want to stress that fulvic acids are lower molecular weight too. They have not as many rings, and even the chains themselves are shorter. So they tend to be smaller molecules. They tend to be lighter, lower molecular weight. They're smaller overall. In between fulvic and humic is this category of ulmic acids that tend to have properties of both. They can be suspended in water. They're not fully soluble in water because they're not quite small enough of a particle size to fully ionize and form, make a true solution. But they're also not so big that they will precipitate out. They'll actually form suspensions in the water. They're not heavy enough in the water to actually fall out of the water, if that makes sense. So ulmic acids are really important for soil chemistry too, but there's not a whole lot of emphasis or a whole lot of information, really, for that matter, placed on ulmic acids. And certainly the lack of information out there is just because it's kind of like this in between humic and fulvic, and therefore it's a little bit of both, and it's kind of more or less of the same thing. But it's interesting because the fulvic fractions have their own distinct properties. The humic fractions have their own distinct properties. And the ulmic seems to kind of straddle and occupy the space between the two of them. So there's more overlap and there's more shared properties between them. So I find that to be interesting and fascinating, even though there's not a ton of information out there about omic acids or what they are. Some people may not even, consider them to be a real thing. So yeah,
That's a really funny way to end that. Yeah, the omic acids in between. You know what? That's going to be the new product. Is going to be omic acid concentrate. And does it come from the sea or does it come? No, I'm just joking. Great episode, Nick. This was fantastic. And where can people find you?
rootedleaf.com. Check us out on Instagram, The Rooted Leaf. If you send me a message on the Growcast Discord, I'm usually pretty good about responding quickly, and I like interacting with everybody. I love the community there. It's been a real pleasure to answer people's questions and help people all along the way. So yeah, I encourage people to give me a shout out on the Discord server if you guys have any questions, any comments. I'm usually pretty active there. So yeah, really appreciate everybody's time, and thanks for listening.
Appreciate you, man. One more time, rootedleaf.com, code GROWCAST for 20% off always. Get yourself the best no pH nutrients. About to do another run, this time in an earth box. And I'm going to see how I can incorporate Rooted Leaf into a SIP system earth box. So stay tuned for that, everybody. Stay tuned for more content. And find everything we're doing at growcastpodcast.com. All the stuff is up there. Thank you to the members again for making this possible. And thank you to each and every one of you listeners. Hope you have a great day in your garden. This is Nick and Jordan signing off saying be safe out there, everybody, and grow smarter. Bye-bye. That's our show. Thank you so much for tuning in. I appreciate all of you. Thank you to Nick from Rooted Leaf. Of course, rootedleaf.com. For the best nutrients around, code GROWCAST saves you 20%. That's right, 20% off. Go and grab them. No need to pH. I just did a run with Rooted Leaf and ProMix, and it was one of the best ones that I've ever done. Loving my Rooted Leaf nutrients. One more time, thank you to Nick from rootedleaf.com. Code GROWCAST, everybody. Helps us keep the lights on, helps Nick, and it helps you in your garden. That's all for now. Thank you so much for tuning in. Make sure you're subscribed. Go to growcastpodcast.com. Whole bunch of new stuff dropping soon. You'll hear all about that. But until then, love you all. Be safe out there. Talk to you next time. Bye-bye.
So stay thirsty, my friends.